All right, so good morning, everyone. I am sorry we had to reschedule from last week. I was actually dying. Um, I spent the whole night coughing, and then the next day I couldn't even speak. It was horrible. Um, Now I'm alive and ready to talk about physics, woo, and some other stuff. So I'm going to go ahead and share my screen with you guys here, and we're going to go over a couple of things. All right, little toolbar. So annoying. Okay. Oh, so first of all, just in case people have not noticed it, there's a huge calendar. Right on the front, when you log into a physical science course, we really don't have too much going on. Friday, there is no school, though. You're not expected to do work. Teachers will not be doing work. It's Veterans Day, so enjoy that time. And then next Tuesday we have, I'm getting feedback, aren't I? Okay. Next Tuesday we have an optional lab. It's really just going to be a time for you to come and ask questions. And I'm going to have a couple of items out for you. I'm going to have some sound works and some Newton spring scales. So you can come physically play with items to help you understand the content. You can come ask questions. You can come do DBAs. You could just come and work and sit next to me if that's what you want to do. But yeah, so next Tuesday there is an optional lab. You're not required to attend that, but hopefully some of you guys will come and ask some questions. And then I added this new thing now in modules where, and that's at 12, yes it is. It's at 12 on Tuesday. Do we have a lot of background noise? I might mute you guys. Not in a rude way, but okay. See if that helps. How do I mute everyone? That's the question. Let's see. Manage participants. Okay. I'm gonna mute you, Annie. Not that you're like screaming or something, but just in case. Okay, that helped with the feedback actually. Sweet. Okay, so now in Module 1 and Module 2, I know a lot of you guys are already almost done with Module 2, but I'm going to start doing this for all the modules. There's now a key vocabulary list content page. So on this page, you'll find not all the vocabulary necessarily. I did leave out a couple of words because they're not really that important, but you will find the most important vocabulary. That's definitely tested on the DBA, that's definitely tested on the tests, and is also just important physics vocabulary to know for if you take a more advanced physics. So you can now find that at the beginning of Module 1 and 2. I'm working on the Module 3 one. Shouldn't take me too long, so I should have it up soon. But they'll all just be posted right at the beginning. So that way, if that helps you when you're taking notes or even when you're studying, just to figure out what's actually important, because there's a lot of silly stuff in this course, which I didn't write it, so I can make fun of it too. Okay, so let us start. We are going to describe the importance of work in physics. We're talking about physics work here, not work. Describe and draw a wave, and we're going to talk about an experiment. It was one of the most life-changing science experiments ever. Because scientists could not decide if light was a wave or a particle, right? And that seems kind of like it wouldn't really make that big of a deal, but it does. We're going to watch a little video about it. So vocab, I just showed you guys this. This is on, okay. This is now on Canvas, right? There's a vocab list. I didn't define the words, but I showed you which words to look for as you go through the lessons. All right, so what is work? I talked to a few of you about this before, so I apologize if you are hearing it again, but oh well. So physics work is different than regular work. I think a lot of people got that. Some people, when they were defining work to me, were like, oh, you know, like homework or going to work. Not the same thing. right? So in physics, work is defined as force times a distance. You are pushing something or pulling something or using something over a distance. Let me make sure I got everyone muted again, right? Looks good. Okay. I heard like rustling, but it could also be my dog. Okay, so an example would be like a machine pulling a heavy box up on a pulley system, right? So if you have a box and you have a string attached to it and it's being pulled up, right? That's work. So I'm gonna ask you guys a little thing to wake your brain up here. Are you doing work right now? Are you doing physics work right now? You can type in the chat if you wanna say yes or no. So are you doing physics work right now? Alina's the only one who said something. Yes, I'm seeing lots of yeses. Are you moving over a distance and applying a force? Ah, when you type. Nice, Christian. That is definitely true, right? Typing could be considered work. You are pushing on the key for a pretty short distance, right? But you are doing work. When you're just sitting there thinking, right, even though that feels like a lot of work sometimes, that's not technically the same type of work here, right? This is one of those things where we have the colloquial meaning of a word, which is what we use like in our everyday conversation, and then we have the science definition, right? So when we're talking about going to work or doing homework or, you know, maybe like doing laundry or something that can feel like work, it's not exactly the same as physics work. Okay, so then in physics work, I put this picture here. This is supposed to be a house on top of a mountain, right? Now, if you're trying to get to that house, there's many ways that you could build a road here, right? Or that you could get there. So if you're starting down here at the bottom of the mountain, you could climb straight up the mountain to the house. That would be the shortest distance, right? You're just climbing straight up the mountain. That's going to be a lot of force, right? I don't know if any of you guys have ever done any rock climbing or mountain climbing. It's extreme, right? So if you lived there, you probably don't want to climb a mountain every day just to go home, right? At least I wouldn't want to do that. Some people might want to. So in physics, we want to think about, okay, well, we don't want to do that much force, right? That's too much work that somebody's having to do to get to that end point. So we could build a road, right? We could build a road straight up. But even then, that's still going to be a lot of force to climb at steep incline. So usually on mountains, what do physicists do? They build roads that go around the mountain and sort of spiral up the mountain to the house, right? You guys might have experienced this too if you've ever driven around in the mountains. Excuse me. The roads don't go straight up the mountain. They curve around slowly, right? So even though we're going to be doing a way longer distance, if we're going all the way around the mountain to get to the top, we're using so little force, right, that we actually end up doing less work. And we could prove that mathematically if we wanted to, but they already have, and that's why they choose to build those kinds of roads. So that's kind of what we're getting at here with physics work, is a lot of it is just problem solving, sort of like, okay, if we have this house up here, how do we get to it with the least amount of force, right, or the least amount of work, depending on what you're sort of going for in that situation. So, work and power, right? Very commonly missed question on the module exam. So if work is distance times force, right? And then here's a guy pushing a lawnmower saying this is work colloquially and scientifically. I thought it was funny. You guys are probably like, okay. But basically, you would call that work colloquially, or when we talk in everyday language, right? You're pushing a lawnmower and it's exhausting. And we would also call that work in physics. Power is how much work is done per time, right? So how long does that work actually take? So that machine that was pulling up a box on a pulley, does that take 5 seconds or does it take 5 hours, right? That's going to matter. If it's taking 5 hours to pull a box up on a string, you probably need to redesign your machine, right? That's not a lot of power going on there. All right, complete topic change to waves. So a wave is a transfer of energy that travels. That's my like simplified definition. You might have written a long, complicated one, but that is the simple one that I'm going to use. The problem is there's a lot of different kinds of waves. So it's hard to get one general definition that sort of encompasses all of them, right? So we have sound waves, we have waves in the water, right? We have light, we have X-rays, like if you get an X-ray taken, those are all types of waves. So some waves, like a sound wave, they travel in something called a medium, or they have to go through something. So if you think about if you bang on a desk, right, or you hit your wall, those sound waves are traveling through that desk or that wall. When you speak, the sound is traveling through air, right, which air is considered to be a medium. If we go to space, there's no mediums there. Space is empty, right? It's a vacuum. So if you try to talk in space, not only would you die, but there would be no sound, right? Because there's no medium for the sound waves to travel on. So you wouldn't hear sound in space, right? Which is very interesting and also difficult to prove. But light and other waves can travel in vacuums, right? They can travel through space. They can travel through anything. And then things like water waves, right, are obviously limited. They have to happen in water, right? So they need a medium as well. For some of you guys, this might be a review. I know some people are just kind of getting into Module 2. Definitely make sure you drew this picture of what a wave looks like, right? Or printed it. You could print one I got this one from Google Images. You could easily print it. And you want to make sure you understand what a wavelength is and what the amplitude is, right? The wavelength is going from a crest to a crest, or a trough to a trough. Those are technical terms, very strange sounding. And then an amplitude is from the center of the wave to the top, right? And those words will become more important later in the unit or in the module. And really, they'll just become more important when you take a more advanced physics class. There's a lot of math involved with waves, if you can believe that. It's almost all math, actually. But they're pretty nice in this course. They don't put a lot of math in there. I think I'm going to rewrite it, though. Next year, there will be math. So you guys avoided the math. Good job. All right. So what are waves, right? There's two main kinds of waves. Mechanical waves that need a medium, like I just talked about, sound, water, right? They have to have something to travel through. And then the electromagnetic waves. Those can travel through a vacuum, right? Usually space, because there's not really other vacuums, but we could make a vacuum. That would be things like light, X-rays, radio waves, right? So radio waves, what you hear music through on the radio, that is an example of an electromagnetic wave. Again, this is just definition-y stuff. You can always go back. I am recording this and pause this and write this down. Or if you're writing it right now, that's awesome, but I know I'm going a little fast. So electromagnetic spectrum, right? This is just describing all the kinds of waves that there are in this spectrum. And these are all things that can travel through vacuums, right? So the main kinds we have are radio waves, which are the biggest waves. Their wavelength, right, or the distance from crest to crest is 10 to the 3, I believe this is in meters. So it's about 1,000 meters from the top of one crest of a radio wave to the crest of another one. You can't even see my hands, right? So radio waves are huge. In fact, here it's showing the size of them. They're like the size of a soccer field, the size of a house, right? Really large. Baseball, that's not a wave. Microwaves. Okay, microwaves are the things that cook your food, right? They are an electromagnetic wave. They're about the size of a baseball. Some of them can be as small as a period on a piece of paper. Uh-oh, I hear people. We got more people in here. All right, sorry, if you're joining, mute yourself or I will mute you. All right. So microwaves are a little bit smaller than radio waves, right? Then we have the infrared rays. These are the kind of rays that allow you to see heat. So if you've ever played one of those video games or seen some of those like movies where they're hunting aliens and stuff, and they have people, you can see the people because they're like red and purple, right? You can see the heat. And they use those special infrared goggles. Guess what? Those are electromagnetic waves. Then we also have, oh, what happened to my chat? Okay. Oh, no worries about being late. All right, so infrared, said those. Visible. Notice how tiny this is in terms of the size and space that visible waves take up. That means light. That's the stuff we actually can see. Out of all of these, we can see this right here. Tiny little bit. We can't see radio waves, we can't see microwaves, we can't see infrared unless we have special goggles, right? But we can see the visible light. These are really tiny waves. They're the size of a bacteria, right? A cell, basically. In fact, they might be smaller. Uh-oh, 1 second. Henrik. No. Sorry, my dog was trying to destroy my shoe. All right, so visible light, we're going to spend a little bit of time talking about today because there was a lot of argument about whether this should even be on this chart, right? Is light even really a wave? We also have ultraviolet light, UV light, right, which insects can see. A lot of bees and other insects can actually see ultraviolet flowers, right? We have X-rays, there's two kinds, and then we have gamma rays, right? So X-rays are the kind that actually go through your body and take a picture of your bones. They're dangerous though, right? X-rays destroy your DNA. They can cause cancer if you have too much exposure to them. That's why they put that heavy lead vest on top of you so that you can protect, a lot of your cells, because X-rays, actually all of these technically, can cause cancer. They break your DNA inside your cells. And then gamma rays are the most dangerous. They're the smallest waves. They travel really, really, well, actually they travel the same speed, but they have a really, really high frequency and they can really, really destroy stuff. All right, that was just my spiel about electromagnetic spectrum. Basically, it's pretty interesting, all these different types of waves, right? They all have some stuff in common. They all travel at the same speed, which we call the speed of light. And that means that there's a pretty obvious relationship here. If they have a shorter wavelength, then they have a higher or greater frequency and they have more energy, right? So if we go back, shorter wavelength here is the gamma rays. They have the highest energy and frequency, which means that they're the most destructive, right? If the wavelength is longer, they have a lower frequency and lower energy. So again, our lowest wavelength here is going to be the radio waves, the least amount of energy, right? You could get hit with radio waves and they're not going to kill you. But if you got hit with gamma rays, they would kill you. All right, so before we move on from this, one last thing. All these things are traveling in space, right? They can all travel in a vacuum. There's nothing really that can stop them. But we do on Earth have an electromagnetic field around Earth, which actually prevents most of these things from getting through, right? Radio waves and some microwaves can get through. Light can get through, infrared can get through, some ultraviolet can get through, but most of the X-rays and gamma rays actually get blocked out by our electromagnetic field, which protects us and keeps us from dying, right? And other planets like Mars, for example, does not have an electromagnetic field. So even if we were able to move to Mars and we thought we were going to colonize it, gamma rays would fly through space and kill you if you made it there safely. So, all right, intense stuff. So then now we're going to move on to this actual question where you guys get to think and not just listen to me talk, although I know some people actually like listening to me talk, so that's cool. But we're going to be answering this question. Is light a wave or a particle? right? And I kind of already told you that now we mostly agree that it's a wave. But back in, I believe this was the 1800s, it might have been early 1900s. I might be completely off on that date, a long time ago. Scientists weren't sure. They were like, what is light? Is it a wave? Is it a particle? Is it both? Does it do some things and not other things? Is it some other thing, right? They had no idea what it was. So we're going to watch this video. This scientist did an experiment called the double slit experiment to try to prove whether light is a wave or a particle. And then after this, we have an exit question. And I'm going to talk a little bit about Canvas technical issues that are no longer allowing me to put exit tickets on Canvas. But regardless, so watch this video and listen to what they're actually doing in the experiment and how this is supposedly proving if light is a wave or a particle.
And here we are, granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity.
So notice that the particles, right, made a whole bunch of little particles, but they were only where the slit was. Whereas the waves, most of the wave is hitting in the center, but part of the wave is still hitting out to the side. So you have like this sort of brightness in the center and then it dims out.
This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. and it goes through just one, and it goes through just the other. All of these possibilities are in super.
All right, so basically, you can tell from this, we're actually going to end the video here. I thought it showed light, but it doesn't. But we'll really quickly find something that does show light. Because basically the concept here is that light does the same thing as the electrons. It creates a banding pattern on the back of the screen, even though it often behaves like a particle, which is really, really confusing. And I remember there was a really good video. All right, I might have to post this because I don't want to spend time trying to find this. But there is also a really cool video where they actually show this with light and with colors and interview people on the street, like what they think is going to happen. And they all think that it's going to just make one line and it makes 2 or 5 or whatever. And it's really interesting. But basically, the concept behind this experiment was that some things behave as waves even though we don't really think they're waves, which can get really complicated, right? And this is really getting into some deep physics stuff that we're not necessarily going to cover in this class. But I kind of misspoke earlier. The conclusion really about light is that light is both a wave and a particle, right? It does both. And that's basically the conclusion that they make about electrons as well. They can behave as a particle or as a wave, depending on what's going on, which is crazy to think about, that electrons can like make decisions and also split and go through like 10 things at once. Very intense. Okay, so that was some heavy stuff there. Next thing is cool and fun. And I'm actually, before we do that, I'm going to change this because we didn't really answer this light question. We're going to come back to that. You're just going to describe the double slit experiment. Okay. So this is a video that's much more just about fun, showing cool stuff that sound waves can do, which I enjoy watching this one because it's just entertaining. Oh, and of course there's an ad.
You don't have to be
I'm
good
sad,
at winter
guys.
sports to enjoy Mount Hood. You can.
YouTube used to not have ads back in 2005 when it first came out. I was around using YouTube ad
that we
free.
perceive with our ears. It makes our favorite music and it keeps us out of danger, but it's so much more than that. Hey everybody, thanks for checking out D-News today. I'm Trace. Now listen up. Sound is extremely powerful. It's made of invisible waves of energy passing through substances, ground, water, air, particle to particle. The human ear can perceive these waves as long as their frequency is between 20 hertz and 20,000 hertz. Anything above or below that, we can't hear, but they're still there because these waves contain energy. And with enough din, you can make these waves do some incredible things. Outside of medical technology like ultrasound, one of the most commonly known ways to make sound do something is by breaking a glass. This works only when the sound wave is at the exact same frequency as the object you're shooting at. If you gently flick a wine glass with your fingernail, you will hear its frequency. Match that tone and turn the volume up, way up to like 11. And that glass will probably break. Also within the range of hearing is sound levitation. This is way cooler than breaking stuff, if you ask me. Sound levitation has been around for years, but until recently, we couldn't do much with the stuff once it was levitated. It just sort of hung there in the air. Thanks to advances at a Swiss university called ETH Zurich, we can not only levitate stuff, but we can move it around, adjusting floating fluids. This works by using the energy in the sound waves. In this apparatus, the energy waves reflect back and forth so quickly they form what's called a standing wave, or a specific point where the energy from the sound can hold an object in midair. Think of it like these silly executive desk toys. The ball in the middle, that's the standing wave. The thing that they just figured out is how to move the stuff once it's levitating. Now they can use this system to manipulate liquids, combining and separating them, all without touching them with human hands, which is immediately applicable to drug manufacturing. That's kind of cool. These energy waves can do a lot of other stuff too. The LRAD, or long-range acoustical device, is a weapon that shoots sound. It's like a sonic death ray, but without the death part. It can produce so much sound that you feel physical pain, like 160 decibels. That's loud. Think NASA rocket launch. But it won't kill you. It just really hurt, like a sonic hurt ray. If you combine some of those technologies, sound can produce really strange effects. In the 1950s, NASA and the US Navy built a device that produces ultra-low frequencies, or ultrasonic sound. If you pointed it at a person and set it to 19 hertz, people would have vision problems and get spots and stuff, because 19 hertz is the resonant frequency of the human eyeball. Kind of like that wine glass example we talked about. If you turn the volume up, people actually would have trouble breathing because the low frequencies were impacting the lungs like energy waves. And if you shot it through the ground, your skeleton would vibrate, causing nausea and joint pain. So which of these sound inventions is your favorite? The levitating ones for drug manufacturing?
So anyway, just some cool stuff that sound waves can do. And really just that a lot of this wave technology is still kind of being developed now, using waves to levitate objects, right? Thinking about that in terms of manufacturing things where you don't want to touch it with your hands because it could be dangerous or because it could be contaminated. Also thinking about using waves in terms of weaponry, right? Especially once you start looking at electromagnetic waves, gamma rays have a lot of potential to be a weapon as well. So pretty interesting stuff going on there. Okay, so what you guys are going to do now, just to end this lesson, oh good, 30 minutes, I was pretty close. I'm going to find, three things. First of all, I'm going to find the video that I thought I was showing where they show light and whether it's a particle or a wave. And I'm going to post that in Module 2 where the vocab is. I've also posted a couple of videos there as well that can help your learning. You can watch that if you're interested in it. If you're not, it's fine. And then second thing, Canvas has this issue where we're using a special tool that allows you guys to sort of join the class at any date, and it spaces out all your assignments for you, which is why like some people aren't on the same lesson, which is great. But because of that, it won't let me add new assignments. So if I try to add this exit ticket, it's going to get erased at midnight. Which is really frustrating. So what I'm going to do is I'm going to just keep track of exit tickets separately. You're just going to email them to me now, right? So you're just going to send me an email, physical science exit ticket, and then I'm just going to, in a spreadsheet, I'm just going to write down if you did them. And at the end of the semester, I'm going to be adding points to people's grades based on how many exit tickets and virtual sessions you attended. So like if you attend none, then you're going to lose points. And if you attended like most of them, then you're going to get some points added to your grade. The other thing is, Kendrick, so yeah, you're going to have to email me your answers to the exit tickets. I'm trying to figure out too, like when we do a lab in person, how that's going to work, just because, yeah, those are getting erased too. So if you haven't been able to do an assignment because it got erased, don't even worry about it for now. I'm possibly also going to just create a lab class to solve this problem, but I don't know. It's a lot to do. Kendrick, stop. All right, so this is the exit ticket. Describe four types of waves you've encountered so far today. Describe the double slit experiment. Just explain what happened in it and why they did it. And then just tell me if you're going to be attending the optional lab next Tuesday, and if yes, if there's anything specific that you would like to work on. Kendrick. Jeez. All right. Sorry, my dog loves recycling, and by that I mean he likes to chew up recycling. Okay, so this is going to be the end of the meeting pretty much, the good old days. Yeah, man, YouTube has so many ads now. Like, I don't even know if I'm going to be able to use it as an educational tool because it irritates me. Although I see why people want to make money, but it's like, come on. I just want to watch a video about sound waves. I don't want to see an ad. So if you have any questions, is the exit ticket in the module? No, I will post it. I don't know where to, actually I can make a content page about it. I will make a content page because those don't get deleted, just assignments get deleted. I will make a content page with the exit ticket so that you can still see it after we end this meeting. And then, yeah, you're just going to email me your answers by tonight. All right. So otherwise, thank you guys for actually, let me make sure I got everyone. I'm going to do a little screenshot of, oh, wow, we got lots of people. Let's see. Just want to make sure I got everyone who attended so I can keep this for attendance purposes. We got Jasmine. Did I get Haley on here? Yep. David. Ariel. All right, I think I got everybody. Awesome. So thank you guys. I hope that helped you kind of understand a little bit more about waves, about physics. Can I excuse you from the sound? Yes, I can. I will put a little star by your name to remember that. Okay. Awesome. So thank you guys for coming, and I will see you soon. Hopefully I'll see some of you on Tuesday at the school. All right. And I'm going to end this meeting. Bye.